Welcome back to Java Internals Crashcasts. I'm your host, Sheila, and today we're continuing our deep dive into the world of concurrent collections. That is, collections designed for use in multi-threaded environments. We're currently in the queues chapter, and we've already covered the BlockingQueue interface, array BlockingQueue, and linked BlockingQueue. Today, we're excited to explore the priority BlockingQueue. Before we jump in, let's start with a quick quiz for our listeners. Victor, would you like to do the honors?
Absolutely, Sheila. Here's a question for our listeners to ponder. In a busy hospital emergency room, patients arrive constantly with varying degrees of urgency. How might a data structure, like the one we're discussing today, be useful in managing the order in which patients are treated?
That's an intriguing question, Victor. It really makes you think about how we prioritize tasks in high-pressure environments. I'm sure our listeners will come up with some interesting ideas. Now, with that thought in mind, let's dive into the priority blocking queue. But first, Victor, could you give us a quick refresher on blocking queues in general?
Certainly, Sheila. A blocking queue is a thread-safe queue that supports operations that wait for the queue to become non-empty when retrieving an element, and wait for space to become available in the queue when storing an element. This makes them particularly useful for producer-consumer scenarios in concurrent programming.
Thanks for that recap, Victor. Now, let's focus on the priority blocking queue. What exactly is it, and how does it differ from the other blocking queue implementations we've discussed?
Great question, Sheila. The priority blocking queue is an unbounded concurrent queue that orders its elements according to their natural order or by a comparator provided at construction time. Unlike array blocking queue or linked blocking queue, which typically follow a first-in, first-out FIFO order, priority blocking queue always retrieves the element with the highest priority first.
That's interesting. So it's not just about when elements were added, but also about their priority. Could you elaborate on how this priority is determined?
Absolutely. By default, the priority blocking queue uses the natural ordering of its elements, which means they must implement the comparable interface. Alternatively, you can provide a custom comparator when creating the queue to define a specific ordering. For example, if you're queuing tasks, you might want to order them based on their urgency or deadline.
I see. So, returning to our hospital analogy, it's like how emergency rooms use triage to determine which patients need immediate attention, regardless of when they arrived. Is that a fair comparison?
That's an excellent analogy, Sheila. Just like in an emergency room where a patient with a life-threatening condition would be treated before someone with a minor injury, regardless of arrival order, the priority blocking queue ensures that the most important elements are processed first.
Now, I'm curious about the internal structure of the priority blocking queue. How does it maintain this priority order efficiently?
The priority blocking queue uses a heap data structure internally. Specifically, it's a binary heap, which allows for efficient insertion and removal of elements while maintaining the priority order. This structure ensures that the highest priority element is always at the root of the heap, ready to be dequeued.
That sounds efficient. But I'm wondering, since it's a concurrent queue, how does it handle thread safety? Are there any specific mechanisms in place?
Great question, Sheila. The priority blocking queue uses a re-entrant lock to ensure thread safety for most operations. However, it's worth noting that the size and contains methods are not guaranteed to be accurate in the presence of concurrent add or remove operations. The queue is also designed to be lock-free for retrieval operations when it's empty.
Interesting. So it seems like there might be some trade-offs between performance and strict consistency. Speaking of performance, how does the priority blocking queue compare to other blocking queue implementations?
You're right about the trade-offs, Sheila. In terms of performance, priority blocking queue operations generally have O log n, time complexity for n queuing and dequeuing, where n is the number of elements in the queue. This is typically slower than array blocking queue or linked blocking queue for basic operations, but the trade-off is the priority ordering. It's also worth noting that priority blocking queue is unbounded, so it can grow as needed, unlike array blocking queue, which has a fixed capacity.
That makes sense. Now, I'm curious about real-world use cases. Where might we see priority blocking queue being used in practice?
Priority blocking queue is often used in scenarios where tasks or messages need to be processed based on their importance or urgency. Some common use cases include 1. Task scheduling systems, where tasks with earlier deadlines are processed first. 2. Event-driven simulations, where events are processed in order of their occurrence time. 3. Network packet processing, where packets with higher priority, like VoIP packets, are handled before lower priority traffic. 4. And of course, as in our earlier analogy, in healthcare systems for patient triage.
Those are great examples, Victor. It really highlights how versatile this data structure can be. Now, are there any common pitfalls or misunderstandings that developers should be aware of when using priority blocking queue?
Absolutely, Sheila. One common misconception is assuming that elements with equal priority will be dequeued in FIFO order. In reality, the order among equal priority elements is not guaranteed. Another pitfall is modifying elements after they've been added to the queue in a way that affects their priority. This can lead to unexpected behavior, as the queue doesn't automatically reorder elements if their priorities change.
Those are important points to keep in mind. Before we wrap up, do you have any best practices or tips for using priority blocking queue effectively?
Certainly. Here are a few tips. 1. Always use immutable objects as elements, or ensure that the properties affecting priority don't change after insertion. 2. Be mindful of the performance impact when using complex comparators. 3. If you need a bounded priority queue, consider using a delay queue or implement your own using priority blocking queue as a base. 4. Remember that size and contains methods may not be accurate in highly concurrent scenarios, so design your code accordingly.
Thank you, Victor. Those are excellent tips. Now, let's circle back to our quiz question. Based on what we've learned about priority blocking queue, how might it be useful in managing patients in a busy emergency room?
Great question, Sheila. In an emergency room scenario, a priority blocking queue could be used to manage the order in which patients are seen by doctors. Each patient could be represented as an object in the queue, with their priority determined by the severity of their condition. The triage nurse would add patients to the queue, and doctors would retrieve the highest priority patient when they're ready to see someone new. This ensures that the most critical cases are always handled first, regardless of when they arrived at the hospital.
That's an excellent application of priority blocking queue, Victor. It really brings home how this data structure can be crucial in real-world, high-stakes scenarios. To summarize what we've covered today: 1. Priority blocking queue is an unbounded concurrent queue that orders elements by priority. 2. It uses a heap data structure internally for efficient priority management. 3. It's thread-safe but has some trade-offs in terms of consistency for size and contains operations. 4. It's useful in scenarios where tasks or messages need to be processed based on importance or urgency. 5. Developers should be cautious about modifying elements after insertion and remember that equal priority elements aren't guaranteed to follow FIFO order. In our next episode, we'll be wrapping up the queues chapter with a summary of what we've learned. Don't forget to subscribe to Java Internals Crashcasts and leave us a rating if you're enjoying the series. Thanks for listening and see you next time.